Hi everybody, welcome back to section 3.1. In this video, we're going to take a look at an exponential growth question. So let's go ahead and read over what we're being asked. So a culture has initially P naught bacteria present. At T equals 1 hours, the number of bacteria is measured to be 3 halves P naught. If the rate of growth is proportional to the number of bacteria present at time t. Determine the time necessary. Determine the time necessary for the number of bacteria to triple. Okay, so let's pick out a couple of things here. So we are given that at t equals 1 hour, the number of bacteria is 3 halves times the initial population. So one thing we have here is a condition, 3 halves P naught. So at time 1 hour, we have this 3 halves times initial population. One thing we also have to find out is the time necessary for the number of bacteria to triple. So this question, what we're being asked is what time, so I'm going to put a question mark there, is going to give us the tripled initial population. Okay, so we know we're dealing with population and exponential growth. So let's go ahead and use what we know about this model. So solution, let's go ahead and set this up. So we know the initial value problem for this situation is dp over det equals k times p, and that at time 0, we have our initial population. Okay, so we know this for a fact, and we know from our work previously that the solution to this IVP initial value problem is what we found previously, that P of t equals the initial population times e to the kt. Okay, we know that for a fact it's always a solution for this differential equation. We found that in the previous video. So let's go ahead and answer the question now. So what are we given? We are given that at 1 hour, the population is 3 halves times the initial population. So we're given that. So let us use this to figure out what K is, our proportional constant. We need that to figure out essentially at what time we tripled the population. So we got to find K first. So let's use what we're given to find K. So what we would do is set it up like this. We would set up 3 halves times initial population equals the initial population, e to the k times 1. So really what I'm doing is taking this condition I'm given and I'm plugging it into my solution. And we're going to figure out what k is. So let's do that. Notice that I have p naughts on both sides. Okay, it's a constant, or it's a number essentially. And so what I can do is just divide that to both sides and they could cancel each other out. So what I'm left with is 3 halves e to the k. Well, we have e to the k, and remember our logarithmic properties that I can take the natural log of both sides to cancel out that exponential and bring down the k. So natural log of e cancels out, and I'm left with natural log of 3 halves equals k. And so if I calculate natural log of 3 halves, go ahead and put in your calculator. but what we get is 0.4055, etc., but we'll cut it off at 4 decimals. Okay, so we have found what k is. So we have that our solution P of t equals P naught. We still don't know what our initial population is, but we really don't need it for this setup. But I'm just going to take this K, plug it into our solution, and that is our setup for our solution. So what we can do now is use this solution that we found to figure out the initial question. At what time am I tripling my population? Okay, so let's figure that out. So now, to find the time in which the number of bacteria tripled, we set our solution equal to 3 times P naught, which is tripling the population, in which we want to find. So let's go ahead and do that. So we're going to take triple the population and plug that into our solution up above, P naught e to 0.4055 t. So what am I doing? I'm taking this and I'm plugging it in right there because the time is what I want to figure out. So let's do that. Once again, the P naughts cancel out. We just divide over each other. And what I'm left with is 3 equals e to the 0.4055 t. And then once again, what we can do is natural log both sides. Okay, the natural log and exponential cancel out. And what we're left with is 3, or natural log of 3, 0.4055 t. Okay, we divide 0.4055 over. Okay, and if you put this in our calculator, right, natural log of 3 divided by 0.4055, we get approximately 2.7 hours. Okay, and that's our answer. So the time necessary for the number of bacteria to triple is approximately 2.71 hours. All right, so that is the time it takes for our population of bacteria to triple. Okay, so here's a graph to the right, kind of displaying the setup of this, and that, here's our initial population, and here's our initial population tripled, and that the time to take our initial population to triple is here at 2.71 hours. Okay, using our solution that we found. Okay, so that is how we would do one of these exponential and growth decay problems, okay? Always got to find your K, and then you got to figure out the time that's being asked or a population that's being asked. But the key reminder here is that we know for a fact that this is our solution to it. We don't have to go out and find it all over again. So just keep that in mind when you do these problems, save yourself some work. And that's it for this video. Take care. I'll see you in the next one. Okay.